So for Lewis dot structures, I'm going to start off with some background. Some of you will already know this. You can skip ahead, of course. Remember that the great thing about these videos is that they pause. I can't go at a real slow speed just because it'll take me forever to make a bunch of these. So feel free to hit pause and have a think. It rewinds. No one will know. That's what's great about videos. Also, write down any questions you have and email me or see me in class and ask. I would suggest you actually write them down, though, because I have done the thing where I show up to class and I can't remember what my question was. So let's talk about electrons on atoms. But before we do that, let's talk about the protons on atoms for just a moment. So for instance, fluorine here has 9 protons. And when we talk about these valence electrons in these Lewis dot diagrams, we're going to say that everything has a charge of 0 because that's pretty much the way it acts. So for example then, fluorine, right, has 9 positive protons. And if the charge is 0, then how many negative electrons does it have? And the answer is 9. 9 positives and 9 negatives make 0. So for the purposes of this, you could just say the proton number is the electron number. There's another wrinkle here, though. It turns out that the way nature works is that these electrons come in energy levels. And just for a quick dirty diagram, we'll do this. Here's the nucleus with the protons and the neutrons of that fluorine. And there's one energy level, and it really is a sphere. So I can't draw a sphere, but let's call it a ring sort of on paper, right? And the maximum number of electrons in this first energy level, or energy shell, sometimes called, is 2 electrons. And that is just the way God made it, or whatever you want to say. It is max 2. It is never any more. It can have 0 or 1 or 2. It cannot have 3, period. Then there's another energy level. And the max energy level of that one, the max number of electrons is 8. And I know I drew it off center, but anyway, it's the next energy shell or energy level. So fluorine has 9 electrons to fit in. So for fluorine, we have the nucleus, and we have 2 in there. And the next energy level, though, does not have all 8 because that would be 10. Remember, we only have 9. So the next energy level has 7 because the 2 and the 7 is the 9 electrons that we said here. And you don't have to draw any of these, and besides, it's not art class and so forth. This is just me illustrating how do I know that the outer shell of the electrons, the outer energy level, has 7 electrons, and it's because of this. This is also called the valence electrons. So what we want to talk about is the outer shell electrons, or the valence electrons. It's the outer shell. The inner shells, frankly, for the purposes of this, do not matter. No one brings it up. How many are in the inside? Don't care. It's not going to help. Figuring that out is pointless. So then this one, notice, has 8 electrons, so that would be 2 and 6. This has 7, so that would be 2 and 5, and it goes back like that. So the whole point of the periodic table being this weird shape with this big gap, this trough often called here, is so that you can do this. You can kind of cheat. It's not cheating, but you can read this. So this one would be 10, right? 2 and 8 would be 10. So these have 8 in their valence shell, except helium, which only has 2. It only has 2 electrons anyway, right? And the reason these are called the noble gases is because they don't associate with the common elements, and they don't do anything. They don't react because they have a complete outer shell. Helium has 2, and that's a complete outer shell 1, because helium doesn't have a shell 2, an energy level 2. And then neon has 8 in its outer shell, and 8 in its outer shell, and 8 in its outer shell. And if you're starting to say, wait, you said 2 and 8, just trust me on this. You don't want me to get into it right now. The whole point is that these noble gases have 8 in their outer shell, and they are super pumped about this. They are the rock stars, the cool kids, and they love the way they are, and they're not giving up their electrons, and they're not sharing anything, and they're not taking on your dumb electrons, because having 8 in your outer shell is the perfect place to be. So everybody else, shut up and get out of here. And these don't react with anything. Now, we said fluorine falls one short of that, right? Because it has 7 in its valence shell, in its outer shell there. So it's going to want to do something about that. And sometimes it steals 1 electron, so that's why it could be -1. And then other times it's willing to share. So what we're going to talk about with these Lewis dot structures is the sharing. And so a shared pair is a bond. So a covalent Notice co together, valence, covalent bond is 2 electrons shared. It's an R. 2 electrons shared. That looks like a Z, doesn't it? 2 electrons shared. And everybody's trying to get 8 electrons except for hydrogen, who is only trying to achieve his nearest noble gas, rockstar hero's position of 2 electrons. So hydrogen is trying to get 2 valence electrons here. And everybody else, all others, are trying to get 8 electrons, 8 valence electrons. Oh, except I should say one more thing. Boron gets bullied. Whoops, that's not how you spell bullied, is it? Bullied. And that often only gets 6 electrons just because it can't manage to steal from its neighbors and get 8. So everybody's trying to get 8 except for hydrogen, and sometimes if boron comes up, it can only get 6 most of the time. It doesn't come up much though, but boron gets bullied, and I think all the times I've seen diagrams with boron and it gets pushed around and it can't get 8, it can only get 6. So what they're going to try to do is share enough electrons that they kind of feel like they have 8 valence electrons, or with hydrogen's case, 2 valence electrons. Now that seems really vague, I know, so let's do some examples. And one of the really simplest ones we can do is HF. So we'll do H and F. So how many valence electrons does hydrogen have? Well, here's another point. We said these have 8 valence electrons, and remember we said 7 here. The whole point of this shape is so you can do this. 8 valence electrons, 7, 6, 5, 4, 3. You got to skip over here and go 2, 1. So this is the I have 1 valence electron column, although we won't actually talk about these whole rectangles here. But hydrogen is in the 1 valence column. What's it trying to get? It's trying to get a complete outer shell. It's trying to get 2, like the nearest noble gas. Fluorine has 7 valence electrons. Don't look at the -1. That's a different thing. Remember we said 8, 7, 6. So it has 7 valence electrons. It's trying to get 8, like the nearest noble gas. Also, let me say that 7, 6, 5, 4, 3 thing only works into the blue section here, not below the blue section, because then I have kids tell me, oh, so lead has 4 valence electrons. Not really. I mean, it's sort of the case, but it wouldn't be useful. So let's just say forget it, and it's not going to help. And we don't do these with metals anyway. And lead is pretty famously a metal. So below the blue stair step here and down into here, or God help us here. No, we're never doing these diagrams with that anyway. So it just breaks down after the blue section, or on the wall in the classroom under the pink section. These are bright pink or something. So let's do this. How many valence electrons does hydrogen have? And we said 1. How many does fluorine have? And we said 7. So let's put them in. And to save ourselves some time, let's point that 1 there. And let's go 1, 2, 3, 4, 5, 6, and let's put that 7th one there. Because what are they going to do? They're going to share a pair, and that's going to bind them together, and that will be a covalent bond. That means that they stuck together, and we have a molecule. So the way most people do it then is we're going to share this pair, and then we join them up into a dash, and that is 2. So any dash is 2, and that's our shared pair right there. So we're almost done with all the preliminaries here. Another thing to say, though, is from their viewpoint, they both think that they own the bond. So what I'm about to do, this diagram is not part of the official answer, but I recommend doing it at least in your mind. Hydrogen says, I own the bond, and therefore I have 2, 1, 2, remember, electrons and valence electrons, and I'm happy because I achieved my spot of having 2 valence electrons like the nearest noble gas. Fluorine views it as, I own the bond, and so you can do this, and it's 2, 4, 6, 8, and it has achieved the goal of having 8 valence electrons like the nearest noble gas. Remember that 10 has the 2 on the inside, right? So don't say, oh no, it's 10. You said 8. It should be 10. No, it's 8. These have 8 valence electrons, except for helium. So everybody's happy and they're bonded and they're sharing a pair, and everybody has their required number of electrons in their outer shell, 2 and 8, and you're done. That's it. So on the next one, another point I would write down is the single atom goes in the middle. So we're going to do H and probably spread these around kind of somewhat symmetrical, would you? I mean, sometimes I see kids throw them all on the bottom, and it's so ugly. Although it's even kind of true, but here, let's do this one. So hydrogen has 1 valence electron. And nitrogen, remember we said we can count backward, 8, 7, 6, 5. So nitrogen has 5 valence electrons. So let's be smart about this and not wear out our erasers. What do I need between here is a pair. So if I take 1 from nitrogen, that can be a bond pair. And 2, that can be a bond pair. And 3, that can be a bond pair. And then somebody's shouting, but you said 5. Right, there are 2 more. So we can do that. Now, if you go look at your molecular geometry paper also, by the way, you might notice, go find the shape that has a central atom, 3 bonds, 3 sticks coming off it, and another little cloud. Maybe I can do that. Another cloud on the central atom. And then that shape is called trigonal, if I can spell, pyramidal. I don't have that paper at the moment. So how about this one? Let's put the single one in the middle. H, 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 H. It doesn't matter if they're in the corners. Some people put them north, south, east, west kind of thing. Let's not argue about that. And hydrogen has 1 valence electron. Let's point them at the carbon so we can not have to erase so much. And then carbon is in our what valence column? 8, 7, 6, 5, 4. So carbon has 4 valence electrons. And look what I have. I need 4 bonds, and they're each missing 1 electron. So that means I need 4 more to fill in the gaps there. And that's perfect because I have 4 more coming from carbon. So 1, that's a bond, 2, 3, 4. And we can do the Venn diagram. Oh yeah, we could have done it here. Nitrogen does this, and I have 2, 4, 6, 8. So that's done. On here, we could do the Venn diagram here. Oh yeah, hydrogen would say 2 there. Hydrogen says I have 2, and then all the same answer. And then carbon says, no, I own the bonds, and I have 2, 4, 6, 8. So carbon is done because carbon has 8 valence electrons. And if you go look on the molecular geometry paper, you have 4 bonds on a central point and no unshared little clouds. So that is tetrahedral. Put the single one in the middle, but the other ones are right around the edges. Fluorine is in the 7 valence column. Nitrogen is in the 5 valence column. So how about we speed this up a little bit, because everybody gets pretty sick of all these dots, and we just use dashes. Every dash is 2, we said, right? So this really is what a lot of people do, and it's even accepted on the AP test. We can just go 2 on the fluorine, 4, 6, and then the 7th one that's pointed at the nitrogen, just so we can use it in a bond in a minute. And 2, 4, 6, 7, and 2, 4, 6, 7. And then nitrogen, we said, has 5. And somebody's shouting, but we only have 3 bonds to make. Right. So we're going to have some extras that aren't used in the bonds. So 1 in a bond, 2 in the bond, 3 and to make a bond, and then 2 more that I didn't use. So maybe you put a cloud, maybe you put a line. Anyway, there are 2 on the nitrogen that are not bonded. Look, we have 3 bonds and a cloud, an unshared pair anyway, on the central atom. That's what we had here, which is why it has the same shape. Trigonal pyramidal. So how about we skip to 7? Now, I should say there is such a thing as a double and triple bond. And that's going to come up right now. So oxygen is O2. So we have oxygen, oxygen. And oxygen is in the 8, 7, 6 valence column. So they both get 6. So how about we do this, though? If that's a 6 and that's a 6, we get 12, right? So how about we not have to erase so much? We get 12, but there has to be at least one bond. We can't have 0 bonds. This thing will fall apart. And we know it's not falling apart. So there's 2. And then we can stick on the rest of the 12. So 2, 4, 6, 8, 10. Because that's 12 total, right? 2, 4, 6, 8, 10, 12 total. Well, it might seem like you're done, but if you do the mental Venn diagram, we get, this one says, I have 2, 4, 6, 8. But this one says 2, 4, 6. I have 2, 4, 6. Also, by the way, it doesn't matter which one gets the all the 3 dashes and which one gets the 2, because if you just look at it from the other side, the right becomes left and so forth. So let's not argue about dumb stuff like that. But one of them is going to have more. One of them has an 8 and one of them has a 6, whichever one. In my case, the left one has a 6 valence set up right now, but we're not done because it needs 8. Now, something that's not boron is going to get grabby. It's going to start stealing. So let's steal 2 of these and share them so that this one kind of co-owns it. It doesn't matter which one you steal, because remember, these electrons are doing laps around the nucleus at light speed, so all these are just a very, very rough idea. They aren't on the top and this side and anything like that anyway, so no matter where you draw them, they're kind of in the wrong spot because they're never sitting still anyway. So just grab a pair, it doesn't matter, and borrow it. And just to show that I don't care, I'll do the top one just so it doesn't match because it doesn't matter. And I'll steal that pair and I'll put it in here. And now they co-own that pair that I just stole right there. So now we get what on the left? 2, 4, 6, 8. And just to double check on the right, we get 2, 4, 6, 8. So everybody has achieved the 8 valence electrons and everybody's happy and you're done. What about N2? So N and N is a 5 valence and a 5 valence, so that's 10 total. So how about we look at it that way? We get 10, and there has to be a bond in the middle, so I guess let's put 2 there so we don't have to erase so much stuff. And I get total of 10, right? And that's 2, 4, 6, 8, 10. Probably easier if you make it even as possible at the beginning. So that's all I get. That's it. Except look. This one is a 6 valence electrons. This one is a 6 valence electrons. So they're both going to steal from each other. And what we get, and just to prove I don't care which one, I'll do it one top, one side. They're both going to steal and then share it. And now everybody Venn diagrams as having 8 valence electrons. In the books, they try to make it a little bit more artistic, and they choose either both top or both side or something. But honestly, it doesn't matter because they're not on top anyway, right? On 9, what you might not know, I don't know why you would know this, nature likes to make carbon strings, and I guess even 2 is a string, so to speak. So what you're going to get is C and C, and then 3 H's on each carbon. They divide up evenly, H, 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 and this, so that these 3 are stuck to this carbon and these 3 are stuck to this carbon. So how many electrons do we get? Valence electrons. Well, I get 4 and 4. Remember, 8, 7, 6, 5, 4 times 2 is 8. So I get 8 here. And then I get 1 each, so that's 6. So I get 14 valence electrons. So that's one way to look at it. And look at all the bonds we got to make. So I got to use 2, 4, 6, 8, 10, 12, 14. Oh, I used them all. So do we need to steal anything like last time? Well, all the hydrogens diagram as a 2 valence, and that they're perfectly happy with that. Oh, also, I will point out that when kids do stuff like this, they go like water, and they go OHH, bond, bond, stuff like this, I know they haven't been paying attention because this hydrogen has 2 and 4 valence electrons because it has 2 bonds. So I would write this down. Hydrogen only ever has a maximum of 2 valence electrons. Hit pause and write that down. This is super wrong. This is called, I know kids haven't been paying any attention. And if that's wrong, wow, some other stuff is going to go badly because hydrogen only has a maximum of 2 electrons. So this is way wrong. So all my hydrogens here have the 2 valence electrons, 2 and 2. What about the carbons? This carbon has 2, 4, 6, 8, and the other one does also. And so everybody's happy and you're done. Well, how about this one? Just, we can't do everything. Let's skip to 11. 2 carbons, and then there are 4 H's. So 2 each. But you know what? We still get a lot of electrons. We get 2 sets of 4 is 8, and then 4 sets of 1 is 4, and so that is 12. So we need 2, 4, 6, 8, 10. But you said we have 12. Yeah, right. We do, and we're going to need it because look at how the carbons diagram when we do the circles. 2, 4, 6. 2, 4, 6, but we have another 2 coming to us. And you know what would solve that is taking the 2 that I haven't used and putting them in the middle so that they count for either one. And now they both count as an 8 valence electron atom, and everybody's happy. I would suggest trying this one and coming back. So hit pause, and when you come back, I'm going to do them kind of quickly. Here we go. It's in this order. I get 1 and 4 and 5, so that is 10 valence electrons. 2, 4. Now, another big mistake, remember, would be go like this, because that hydrogen now has 4, and that's never going to happen in the life of the universe, so that's wrong. So 2, 4, 6, 8, 10 or something? Sure. Somewhere anyway, right? But the carbon is happy because it has 8 valence electrons, but the nitrogen is super unhappy. It's not going to be remotely okay with 4. It's going to get stealing. So we have to steal a pair and put it in the middle. But nitrogen still is only at 6, so it steals another pair off a carbon. And we have a triple bond. Carbon dioxide has C in the middle, O's on the end, and we get 4 and 2 sets of 6 is 12. So we get 16 total valence electrons. So we got to use 2, 4 just to have some bonds at all. And then I said 12 more, right? So 2, 4, 6, 8, 10, 12 more, I guess. Somewhere anyway. But everybody in here wants to have 8. The carbon only has 4. Not going to happen. Again, not remotely. So steal a pair, and I don't care which one. I'll steal this one. Put it in there. Now the carbon is at 6, but it's going to get stealing. But the other side is easier to steal from now, so steal a different pair. And just to show it doesn't matter, I'll steal the top one. And now everybody, when you put a circle around them, has 8, because you would do like this, 2, 4, 6, 8. 2, 4, 6, 8, because remember, everybody thinks that they own the shared pairs. So another thing to notice is that's a minus sign. I know it's probably really small on the camera. That's a minus sign. So that's -1. A -1, I would write this down, means you get a free electron, and you're going to need it. That's why you have it. Not because we think you should have it, but because nature is trying to achieve something here, and to do it, it stole an electron. So there you have a stolen electron in here. So let's do this. C, N, and that's a 4 valence, and that's a 5 valence, except we get an extra one, right? And nature really likes these things to happen in pairs. And so how about to save some time in erasing down here, how about we just count that as a 6? There's my extra one. My stolen one is added in now. And we count nitrogen as a 6. And okay, we have 10. We have 10 we can work with. So we got to have 1 bond. So that's 2. And then just put some stuff down and we'll see where we get. So 2, 4, 6, 8, 10. There we go. But guess what? Everybody has 6 valence electrons. It keeps happening here for a while, right? Partly I kind of designed it that way. So everybody gets stealing. They both steal off of each other and put them in the middle. And cyanide ion, which is very famous for being extremely poisonous, has a triple bond. Here's another point, though. Pay attention. There was the free electron. And so if somebody looks at this, they could say, wait a minute, C and N should be 9 and you have 10. So what we're going to do, and this is required, I get to mark stuff off on this, right, is brackets and -1, which says to the reader, I know there's an extra electron. Seriously, there is one. I'm not just making this up because I felt like it, because I don't know what I'm doing. Which tells us on 18, you get 3 extra electrons. On this, you get 1 extra electron. On this one, you get 2 extra electrons. Also, I will point out on 31, plus means you have an electron missing. In fact, how about we do this one? And in the middle, H, 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 H. And so that's a 5 valence, and that's 1 set each, so 1 electron each, so that's 4. So that's 9. But we're missing 1, so it's 8. And how many do we need to make these bonds? We need 2, 4, 6, 8. Oh, look, hey, that's great. Double check, though. Does the nitrogen feel like it has 8? 2, 4, 6, 8. It does. And that's why it's missing, because sort of the nature didn't know what to do with the 9th electron, so it just kind of gave it away. And then because it's charged, again, we put brackets and we put a plus sign on it. We're not just making it up. Seriously, it's +1. There is 1 missing on purpose. I know what I'm doing. Oh yeah, so that one gets an extra electron. That one gets an extra electron. That one gets an extra electron. So next step up would be something like 21. And this gets a little kind of hairy. So pay attention. The single one goes in the middle. O, O, O. And so that's a 5, and that's 3 sets of 6 is 18. And we get an extra one. So 19 and 5 is 24, right? So you could do it that way. Or how about this? Piece of advice, when you have oxygens and chlorines and stuff around the outside, what I tend to do is just put the ones on the outside and then deal with the middle. So you can do 24, and that's fine. How about this? We do 2, 4, 6, 2, 4, 6, 2, 4, 6, because that's what the oxygens have. And then I've used up all the oxygen ones. And then nitrogen, is a 5, but I get a freebie, so it's a 6, so to speak. Then some kid says, which one's free? It doesn't matter. They're all the same. You have a free one. It doesn't matter that you keep track of which one's free. So I need a bond, so that's 2. Bond, so that's 4. Bond, so that's 6. And here comes the interesting part. We are out of electrons. We used the 18 on the oxygens, and we used the 6 on the nitrogen, and that's it. We're out of them. We don't get any more. And the catch to that is nitrogen feels like it has 2, 4, 6 electrons. And well, it's going to get stealing. You're right. It's going to get stealing. But here's the trick. It can steal from any one of these 3 oxygens, and they're all equally attractive. So my phrase is, when the choices are equal, it chooses equally. And I wish I understood this next part better. Someday somebody can get a chem degree and come back and tell me exactly how this works. But you're just going to have to believe me. When the choices are equal, it chooses equally. Well, it wants a double bond. Remember when we had 6, it started stealing on the other side? Yeah, you're right. What it does, apparently, is it steals pulls one of these pairs partly this way, and one of these pairs partly this way, and one of these pairs partly this way, and it effectively makes a partial double bond on each oxygen, with each oxygen. So when I was in college, they made me double bond it here and then rewrite the whole thing, double bond it here, and rewrite the whole thing and double bond it here. And I think that's a big pain in the neck, and it also wastes my paper space. So I'm going to do this. Pick one of them. I don't care which one. And then pick a pair on that atom. I don't care which one. And steal it. I'm going to pick this one at random. I don't care. And I'm going to steal it. I'm going to put it in here. And now the nitrogen has 2, 4, 6, 8. Except there is one more thing. It really is doing a 1/3 double bond here and 1/3 here and 1/3 here. And that is called a weird name, which is a resonance structure. Resonance, not renaissance. Resonance structure. And I'm going to run out of room here and go over into the box. Okay. And the reason for all you people who are thinking that is a stupid name for that is that once upon a time, scientists thought that it was double bonding here and then 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 here. And going back and forth is resonating. So it got named resonance structure, and now we're kind of just stuck with the name, even though no one believes that anymore. It's been basically proven that it's double bonding in all cases a little bit at the same time, and it's not flipping back and forth. But we still write resonance structure. So you tell me, yeah, I know it's choosing equally, and I'll let you out of having to rewrite the whole thing many times. I'm going to do one more at the moment. Ozone. This is the stuff that you hear about in the ozone layer, although actually it's a pollutant at ground level. It's a bad idea. Notice that it's 3 O's, and O2 is what you want to breathe, and this has an extra one. So this is kind of an unhappy molecule, by the way, and it's always trying to ditch one of these oxygens and stick it on something else, like your mouth or your lung tissue or your trachea, which is a bad idea, or rubber or plastic. So it tends to break down rubber or plastic, so that's another reason not to have it at ground level. So it's a pollutant at ground level. Anyway, I will tell you, I like to ask this question on quizzes, and even though I put it on homework like 3 times and make a big deal of it on the board, I have people who botch it up. So pay attention, kiddies. I get 6 valence electrons 3 times, so that is 18. I get 18 valence electrons total. Well, I got to have a bond here, so that's 2. I got to have a bond here, so that's 4, and then throw some in there. It's probably easier if you go to the ends also. Start at the ends, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, I ran out of room on the ends, so 18 there. So if we Venn diagram the sides, we get 2, 4, 6, 8, and the same here. So those are happy, but the middle one is unhappy. It has 2, 4, 6, and it's going to get stealing. But the choices to steal from are equally attractive, so it's going to do a half double bond with each. And I don't care which one you pick, left or right. I'm going to pick left just because I kind of picked right there. And then I don't care which one you pick to steal. I'm going to pick the bottom for no good reason. And I'm going to steal that one and put it in here. But really, it's stealing like half of this one and half of that one or something like that. But instead of writing out both versions, I'm going to say pick one, steal from it, put it in the middle, and then tell me it's a resonance structure so that I know that you know that really it's partial double bonds in both directions.